This project is about state estimation and sensor fusion on ARM Cortex-M processor. There are three applications in this project: tracking with Kalman filter, estimation with recursive least squares, and estimating passive suspension with Kalman filter. The processor is STM32F4. I used Kyle Macrovision 5 to develop the project. As a programming language, I use C++14 to implement the algorithms. Unfortunately, Kyle Macrovision 5 does not officially support C++17. The FreeRTOS is the real-time operating system in this project, and for communication between embedded device and PC, I use TCP socket to send and receive data. The library that I have chosen to use for network programming is LWIP. Also, the project has various types of tests that I will show them later in this video. This is the source code of the project in the Kyle Macrovision 5, including C++ classes and header files. Also, there are some classes for testing the application. If you want to run the unit test, you have to define test env for the project. If I run the application, you can see the results of the test in the console. There is no need to run the integration test on the hardware. I run them on my Windows. First, I have to build the project. Then I can run and see the results. For more information about the tests, you can see the README of the project on GitHub page. Now we want to run the first application, tracking with Kalman filter. In the interface application, we can draw a path and then add measurements with some noise. The black circles are the measurements that we want for the ARM processor as an input. We can set the initial position of the object by mouse, and then we will run the application. The orange line is the estimated result of the Kalman filter. The next application is recursive least squares. We have two chemical liquid in a tank. This is the measurement equation. You can see other equations in the description. The problem set is from example 3.5 of Optimal State Estimation Kalman Filter book written by Dan Simon. The values of x are 10 and 5. We set the initial value to 8 and 7, and we will see the result that how long it takes to reach the exact values. The last application is estimating passive suspension with Kalman filter. In the interface application, we can choose the IP, the port, and the simulation time in seconds. Here you can see the result. The black lines are the ground truth and the red lines are the estimated result. The important note here is that we have just one sensor on the suspension part, and we do not have any sensor on the wheel. So you can see the estimated result on the suspension part is more accurate than the wheel part.